A projectile is any object moving through the air that is only the force of gravity acting on it. Now, of course, there'll be air resistance acting on the object too, but in these cases only the downward force of gravity is to be considered. So in the case of throwing a ball straight up, the force of gravity is the only force acting on the ball once it leaves the thrower's arm. So we define a projectile then as motion of an object which is only the force of gravity acting on it. So an object thrown straight up is a projectile motion. We also can have projectile motion if something is kicked at an angle. If a ball is kicked at an angle, then once the ball leaves the foot of the kicker, there's only one force acting on the ball, and that is the force of gravity. So that is a projectile too. The kind of projectiles we'll be studying is these ones here, when something is kicked horizontally. Now once again, if something is kicked horizontally, then the only force acting on that ball once it's kicked and once it's moving in the air is the force of gravity. So we say that is a projectile. And the ones we'll be studying is this type here, which is called the horizontal projectile motion. Now we'll have to study how projectiles in fact move, and to do that we have to simulate them and do experiments on them to find out what happens to the horizontal velocity and what happens to the vertical velocity. We can have a bit of a guess here. We know that if the force of gravity is the only force acting on a horizontal projectile, then it's going to have only one acceleration, and that's going to be a downward acceleration. It'll have no acceleration in the horizontal direction because there's no force acting in the horizontal direction. So let's study these projectiles more in detail. Let's study the motion of a horizontal projectile, in this case a ball being rolled off the top of the table. The white sphere represents the ball, and you can see there's an arrow coming from the white ball. Now that arrow represents the horizontal component of the ball's velocity. You don't see the vertical component of the ball's velocity yet because the ball has not yet been rolled off the table. But let's roll the ball off the table, and before we do that we can actually change the horizontal velocity of the ball by using this little slider here. We can go from a minimum horizontal velocity right the way up to a maximum horizontal velocity. So we'll see what happens when we change these velocities. So we'll start off at the minimum horizontal velocity of the ball being pushed off the table, and let's see what happens. Now you can see that the horizontal component of the velocity of the ball, which is that green arrow, that green vector, doesn't change. And that is actually backed up by the graph of the horizontal component of velocity. You can see that throughout the journey it was 5 meters per second. So the ball was launched off that table with a horizontal velocity of 5 meters per second. It didn't accelerate. But if you look at the vertical component, the blue arrow, you can see, or you had seen, that it started off very small and yet it increased in size as it went down. This was telling us that the vertical component of velocity was increasing as time goes on. And that's what we expected, because the projectile is under the influence of the force of gravity, which causes it to accelerate downwards, thus increasing its velocity. So you can see that from the vertical component of velocity graph. As the time went on, the vertical velocity component increased. And that's in line with our definition of a projectile. You can also see that the path taken by the ball is a very famous one. It's called a parabola. And also take a note of the time to land. It took 2 seconds for the ball to land. Now we're going to reset this now and use a mid velocity to see what happens. So we'll take the velocity up to about a wee bit higher, a mid value. And you can see that corresponding horizontal component of velocity, the green vector, increasing in size. Now let's run and see what happens to two graphs. And there it goes. We have the path being that famous parabola. But once again, the horizontal component of velocity stays the same because there's no acceleration in the horizontal direction. But in the vertical direction, the vertical component of velocity increases due to the acceleration of gravity. Now, an important thing to note is this. It still took the same time to land, 2 seconds. So even though we increased our horizontal velocity, it didn't have any effect on the time it took to land. It seems that the time it takes to land just depends on how high up the ball was to begin with. So let's reset things and go to our top velocity and see if it changes anything. We'll increase our velocity to its maximum. That's represented by a longer green vector representing the horizontal velocity component of the ball. Let's run, and you can see that the minute we begin to run, the vertical component increases all the way down. The horizontal component does not increase. Our new top velocity of 19 meters per second horizontally doesn't change. That's because there's no horizontal acceleration or horizontal forces taking place. But vertically, as we defined in a projectile, the only force acting on it is the force due to gravity, which causes it to accelerate downwards, increasing its velocity. And you can see that on the little chart representing the vertical component of velocity. Its velocity increases, and that straight line is a well-known straight line, and we know that we have got a constant acceleration if we get a velocity time graph like that. But the surprising point is, yet again, we started off with a low velocity. The time it took to land was 2 seconds. We increased the horizontal velocity. It still took 2 seconds to land. And we gave it the maximum horizontal velocity, and it still took 2 seconds to land. So, the time it takes for a projectile to land, if it's a horizontal projectile, doesn't depend on its horizontal velocity at all. Now, what we're seeing here is two distinctive motions taking place. We're seeing a horizontal motion, which has got no acceleration, constant velocity, and we're seeing a vertical motion, which has got an acceleration due to the force of gravity. And these two motions combined give the very famous parabola shape to a horizontal projectile. Here we have the two graphs of the vertical velocity component and the horizontal velocity component of a horizontal projectile. We know what happens. The horizontal velocity stays the same. In this case, it was launched off the table with a horizontal speed of 12 meters per second. And we're going to use the word speed now rather than velocity to make things a bit easier for ourselves. Remember, velocity is a vector which has got size and magnitude, and speed is really the size of the vector. So from now on, I'll just refer to these as the vertical speed graph and the horizontal speed graph, just giving us the sizes of the velocities. So we can see then that the horizontal speed launched by that projectile off the top of the table is 12 meters per second, and it landed 2 seconds later. The vertical speed of the projectile increases as it goes down because of the acceleration due to gravity. Remember, a projectile is defined as an object, once it's moving, has only one force acting on it, and that's the force of gravity, which produces an acceleration acting downwards. Now, from these two graphs, we can see that the projectile landed 2 seconds after it was launched. And the graphs tell us a very important thing. We remember from our dynamics that the area under a speed time graph is equal to the distance gone. So in the case of the horizontal speed, the distance gone must be the range of the projectile. That's the horizontal distance it travelled. And that can be found by just shading in the area under the horizontal velocity or the horizontal speed time graph. So you can see that area, if we work it out, the area is going to be equal to a rectangle, and it's going to be 2 times 12. So the area becomes 24, and therefore the range, the horizontal distance travelled by the projectile, will be equal to 24 meters. So we know the range is 24 meters, and it's that easy to find. Now, what about the vertical velocity then? Well, the vertical velocity or the vertical speed time graph, the area underneath it, is going to tell us the vertical distance the projectile travelled. And really that's its height when you think about it. It travelled from here down to here in a vertical manner. So the area under the vertical speed time graph is really the height at which the projectile was released from. And that's easy to find because you just need to work out the area of that triangle. And the area is 1/2 times the base times the height, which is 19.6. And that's going to give us an area equal to 19.6 metres. So the height which the projectile was launched from is 19.6 metres. So to recap, once you get the vertical speed time graph of the projectile and a horizontal speed time graph of the projectile, just by finding the area under the graph, you can work out the height the projectile was released from, and you can work out the horizontal distance travelled by the projectile, which is called its range.